as I told you, and I will tell you every class, everybody should be in possession of a notebook and pen so that you should be able to note down it. Okay, and try to attend with same attentiveness till the last. If you miss one point in the middle or in this last, that may be affecting you while solving the numericals. Okay, in the numerical sessions. That's why. So you have to be very careful. Now let us start with the today's topic, buffer solution. What topic? Buffer solution. Okay. So buffer solutions are the solution which resist. Buffer solutions are the solution which resist change in pH. Which resist change in pH on addition of small amount of acid or base or water. Okay. So normally when you add acid to the normal solution other than the buffer solution, when you add acid, pH decreases. When you add acid, what happens? pH will decrease. Okay, because number of H positive, concentration of H positive will increase, and there is a, so people will think that this is also one misconcept, negative log of H plus. This and this both are directly proportional, but don't forget that this is negative sign. Okay, so because of this negative sign, if I am writing over here, it will become inversely proportional or not. Okay. So when acid is added, that means we are adding H plus. So denominator is increasing. So total value will decrease. That is one thing. And if I add 10 times, if I add H positive 10 times, not plus 10, it is 10 times. Okay. When it is 10 times, it will increase by 1 time. Okay, so like 1 molarity is made 10 molarity, then there is a change in pH of 1 if it is 1 liter. Okay, so we can change the concentration in two methods, just by changing the molarity or by changing the number of moles of H positive or by changing the volume. Okay, so you should be keeping two things into your mind. pH is not directly proportional, it is inverse proportional, and not simply inverse proportional, it is inverse proportional to log of concentration of H plus. That means 10 times leads to 1, 100 times leads to change of 2, 1000 times leads to change of 3. Okay, so this is because of the application of log. Log 10 is equal to 1, log 100 equal to 2, log 1000 equal to 3. Okay, so this misconcept I think everybody now understood. So if you understand this acid, then it will be easy for you to apply it. It will be easy for you to apply it on the base also. Okay, so once you are adding acid, you are increasing H plus. When you add base, so base means it will be OH minus, so it will go and reduce the H positive, reduce the H positive. Just now I told you it is pH is completely depend on H positive only. Okay, so and it is completely inversely proportional to logarithmic value of H plus. So OH minus will go and reduce the amount of H positive available. So denominator is reduced, total value will increase. Here also same, but there I used in the acid I used the decreased term. Here I will use increased term. Okay. So OH minus when it is added, suppose H positive decreases by amount of the H positive decreases by 10 times. Okay. Then pH will increase by 1 time. When OH minus is added, H positive concentration decreases by 1000 times, pH value will increase by 1 time. Okay. Now same way, case with the pH with water. Okay. So this is different condition. All the three conditions, all the three differences. Here it is due to increase in H positive. It is due to decrease in concentration of H positive. Here when you add water, number of H positive will remain same, but volume. Suppose there was number of moles are 1. Okay, and volume was 1 liter. So molarity will be how much? 1. So here I will substitute 1. But when I add water, I am not increasing the number of H positive, but I am increasing the volume of solution. Suppose I have added 99 liter to the solution. Then numerator part of the molarity will remain same and denominator will become now 100. 99 I have added previously 1. Okay. So now molarity will become 0.01. What it will become? 0.01. Okay. So now pH will, see, earlier it was concentration was 1. Now it is concentration is 0.01. So this concentration denominator decreasing, total value will increase. That's why water increases. Okay. So it is, water is not changing the quantity of H plus. Here quantity of H plus increased. Here quantity of H plus decreased. Here volume of solution increased. Okay. So but these are all things are going to affect their pH. Understood? Way of understanding normal solution understood now. Okay, so this is about the normal solution. Any doubt about this? I don't think you got any doubt as of now. Okay, there are certain solution which does not happen all these things. Okay, there are certain solution which does not happen all these things in which they do not happen. Okay, so those things are only called as buffer solution. Those things are only called as buffer solution. When you add acid, no change. When you add base, no change. When you add water, no change. Such type of typical solutions are called as buffer solution. Okay. So buffer solutions are solution which resist change in pH on addition of small amount of acid or base or water. Okay. This is about the buffer solution. I don't think now definition is clear. Now there is one more word. Resist change I made you to understand. There is one more word you should keep it in mind is small amount. Up to what amount it can resist. That capacity will be there for the different solution. Different solution for the small amount quantity will be changing. Higher the amount to which it can resist, higher will be something. That something is called as a buffer capacity. Okay, buffer capacity. Some solutions have more buffer capacity. That means they can resist to a large amount of acid, base or water. If their buffer capacity is less, then they will start changing their pH on addition of small amount of acid or base. Okay, so higher the buffer capacity, higher the ability to resist the change in pH. It is a measure of buffer capacity is a measure of resisting change in pH. Measure of resisting change in pH to which it can to which extent it can avoid changing pH. Understood? So buffer capacity more, that means we can add more amount of acid, more amount of base, more amount of water without causing any change in its pH. Is it understood? Okay. Now this is about the buffer capacity definition part and concept part. Okay. So now we will understand the types of buffer solution. Now what we will do? We will do the types of buffer solution. Okay. So buffer solutions are specially divided into two types. Okay. Buffer solutions are specially divided into two types. Okay. So first one is called as simple buffer. First one is called simple buffer. Okay. Second one is called mixed buffer. Okay. Second one is called mixed buffer. Understood? Now, so mixed simple buffer means it is a only one compound. What it is? It is only one compound. Okay. Either weak acid. Okay. Examples are weak acid. Okay. Second example is weak base. So they should be either weak acid or they should be either weak base. As the word itself is here, they don't have tendency to lose H plus. They don't have tendency to lose OH minus. They are adamant. They cannot lose H plus more. They cannot lose OH minus more. Therefore, obviously, their pH will be constant. Obviously, what happens? Their pH remains constant. It is because of their inability, it is their adamancy to not to release more H plus, not to release OH minus. Okay, you do anything, but their ability is fixed there only. Okay, they are fixed their mindset that they don't want to lose H plus, they don't want to lose OH minus. So because of that, they are called as a buffer. There is nobody around it. That's why it is called as a simple buffer. Simple buffer is a only one molecule. Okay, simple buffer is only one molecule. Okay, now coming to the mixed buffer. Coming to the mixed buffer. So as in the chemistry, most of the things will be prompted to you in the heading itself. If you understand the heading, 90% of the thing you are understood. Okay, so mixed means at least how many things should be there? Two things should be there. Okay. Now it is a two things. There are again divided into two types. Okay. Acidic buffer. First thing is acidic buffer. Okay. And second example is basic buffer. Okay. Second example will be basic buffer. Okay. So these are the two examples, two types. Okay. What are these? These are the two types. So in these two types, again there will be how many parts? Parts is different and types is different. Okay. So parts are two and here types are also two. So that's why don't get confused with parts and types. Okay. So in each every type there will be two parts. Okay. This is a type, this is a type. This is a type and this is a type. Again parts will be how many? Two parts. Okay. Acidic bar Acidic buffer contains two parts. Basic buffer also will contain two parts. Okay. So if I explain this, I think it should be well understood. Okay. Acidic buffer is simply weak acid. First part is, it is part, not type. Okay. Weak acid. And second part is salt. Okay. But this salt should be made from the same weak acid. Okay. Salt should be made from the weak acid. But for making salt of acid, what we require? We require some base. Okay. So that base is strong base. That base is strong base. Salt made from the this acid, and for making that acid into the salt, what we require? Some base. That base we should select which is strong enough. Okay, the base we select should be strong enough. Okay, then only it will be able to, form the buffer, because one part is required strong, one part is required weak. Then only it will be able to maintain that pH sufficiently high. Okay, so that pH sufficiently high should be maintained. Then for that we require both ends. Strong is required, weak is required. Who is strong here? Acid. Who is weak here? Acid. Who is strong here? Base. Now if you understand this, then definitely you will be going to understand the basic buffer also. Okay. So this example I will give you, CH3COOH is the weak acid. Okay. Now the salt which I am going to produce is from the same, but the base I should use which should be strong enough. So here when I add the base like KOH, then the salt will be formed CH3COOK. Okay. So this is the example. This mixture is an example of acidic buffer. This mixture is an example of acidic buffer. Okay. Now coming to the basic buffer. Okay. So basic buffer also will contain how many parts? Two parts. Okay. Basic buffer itself is a type, second type of buffer. Basic buffer itself is a second type of buffer. Okay. And further it is going to contain how many? It is going to contain two parts. Okay. Every buffer, if it is a mixed, will contain two parts. Every buffer, if it is a simple buffer, consists only one part. Okay. Now basic buffer will again be made divided into how many parts? Two parts. Like here it was weak acid, it will be what? Weak base. Okay. So weak base example is NH4OH. Okay. Weak base example. What is weak base example? NH4OH. Okay, and we can use here, as in the previous example we took, what we took example of, here as strong base. Now we are going to take an example of strong acid. Okay, here same salt should be made, but here we made salt from the weak acid, but here we are going to make salt from the weak base, salt of same weak base. Okay, salt of same weak base, but this time we should select with strong acid. Okay, strong acid. So for this strong acid, suppose sulfuric acid, if I am taking NH4 twice SO4. Okay, this both collectively called as basic buffer, both collectively called as basic buffer. Okay, this is the theory part of the types of buffer solution. Buffer solutions are, broadly if you take, there are four: weak acid, weak base, acidic buffer, basic buffer. Okay, and if you divide into sets, then there will be how many types? Two types: simple buffer and mixed buffer. Okay, so in the simple buffer two types, mixed buffer two types, and mixed buffer two parts. Okay, now there is no formula required to find out pH of weak acid and weak base. It can be simply found by using pH scale, but it is difficult for us to find the pH of mixed buffer because it is a mixture. Okay, so for that Henderson Hables. Okay, so Henderson gave an equation that is called as Henderson equation. Henderson's equation. Okay, so Henderson's equation is different for different types of buffer. Okay, so first let us take for the acidic buffer. Let us take for the acidic buffer. Okay, so in acidic buffer, pH must be equal to, here as I told you, it consists of weak acid. What it consists? Weak acid. That's why we will take pKa. Okay, plus log of concentration of salt. Log of concentration of salt divided by concentration of acid. Okay, so this is the formula to find out pH of acidic buffer. Okay, Ka is dissociation constant of acid, and there you have to take negative log of it, then you will get pKa plus log in concentration of salt upon acid. Okay, now same way, next is going to be for the basic buffer. Next is going to be for what? Basic buffer. Okay, so basic buffer, as in acidic buffer we studied pH. Basic buffer, what we will study? pOH. pOH is equal to pKb plus log of salt will be common. Okay, and in place of acid we replaced pH with pOH, therefore we should replace acid with the base. Okay, these are the two different formulas used depending upon the type of buffer we have. Okay, these are the two different formulas we should use depending upon the type of buffer we have. Okay, acidic buffer this formula, basic buffer this formula. Is it understood? Now this is numericals related to these. We will discuss afterwards in the numerical session. Okay. So every session got its own importance. For better score, you should attend both of them and you should try to make a note of it. Okay. Now after the Henderson equation, how the buffers are formed. How the buffers are formed. Okay. So let us take an example. Okay, CH3COOH plus NaOH. Will it make a buffer or not? May or may not. That purely depends upon the quantity. Okay. Now, first I am taking case of 100 ml. 100 ml and zero point 0.1 molarity. Okay, this is the first condition, and this is the acid I am taking. Okay, now here also 100 ml and zero point 0.1 molarity. Okay, so then will it form buffer or not? Here question is, will it form buffer or not? Okay, so here we should compare, we should have left with two things. What are those two things? Acid and salt. Both should be available. Here, when they both, stoichiometry suggests that both should be 1 mole for complete reaction. Okay, both should be what? 1 mole for complete reaction. Okay, so here 100 into zero point 0.1 molarity. Okay, molarity into volume, you will get moles. Okay, but here 100 ml are there, therefore what we need to do, we need to convert into liter. This is also 0.1, 0.1 into 0.1, then we will get 0.01 moles of acid is there, and here 100 into zero point 0.1, 0.01 moles of base is there. Okay, so when same quantity of acid and base both are available, okay, both quantities are available, then complete neutralization will take place. Only salt will be left over. What will be left over? Only salt will be left over. For a substance to be a buffer, what should be there along with the salt? What is that salt? It is going to form CH3COONA. Will it make a buffer? No, because for buffer how many things are required? Two things are required. We got only one part of the buffer, salt. Acid is not left over. Is it understood? So this is the first thing. Now I am taking another example of 100 ml of acid and zero point 0.1 molarity. Okay, here 100 ml and 0.1 molarity. Okay, so in this condition will it form or not? Let me check. Here on multiplication, like previous condition, it is 0.02, and here on multiplication it is going to be 0.01. So a neutralization will takes place. Okay, neutralization will takes place, and which is limiting reagent? This is limiting reagent. The product formed will be according to limiting reagent. Okay, here salt will be formed. What is that salt? CH3COONA. How much it is? 0.01 salt. Okay, and what will be the condition of acid is leftover excess? Okay, so acid is left over in excess. How much acid? Acid is left over. How much? 0.01 of this one is reacted with this one. So how much is left over? 0.01 will be still left over. Okay. So that means here we got how many things? Two things. We got salt also. We are left over with weak acid also. Okay. Now this is necessary and sufficient condition for formation of buffer. A buffer is said to be formed only when acid, weak acid and its salt both are collectively available. Okay. Now let us take the reciprocative condition. Other condition, here I am taking, sorry, here it is 200 ml. Okay. Now this calculation I have taken this 200 ml. Okay. Then it will be zero point 0.02. Okay. This you make it as 200 ml. Now I am making this to 100 ml and zero point 0.1 molarity. Okay, and here I am taking 200 ml. 200 ml. Okay, here I am taking what? 200 ml. Okay, so 200 ml and same zero point 0.1 molarity. Now this is going to give you 0.01 moles. 0.01 moles. Okay. 0.01 moles, and here it is going to give you how much? 0.02 moles. Okay, 0.02 moles. Is it understood? Now when you combine here, which is limiting? Acid is limiting, so but salt will be formed. Again salt is same salt, which is CH3COONA. Okay, how much salt will be formed? 0.01. And what is left over here? Base will be left over. Okay. plus base, which is strong base. Both strong. Okay, salt with strong can never be a buffer. Okay, so what salt will be the leftover? NaOH salt will be leftover. Okay, here salt. Salt will be formed, which is NaOH. Okay, this is also 0.01. So salt base, salt and strong base cannot make a buffer. Salt and strong base cannot make a buffer. Here one condition is satisfied, mixed, but other condition it is not able to satisfy. That is, one of them must be weak. Here weak base, if it is there, then it could have been a buffer. Is it understood? So examples of buffer formation. I think everybody understood. This is about the formation of buffer will take place or not. This is an example where different quantities will result in different type of substances. Out of the three conditions, only one condition is dealing with buffer. That is, amount of weak acid must be more than the amount of salt. Okay. Okay. First is both. First condition is both acid and base are equal. So there is no limiting reagent, no reactant will be left over. Okay. So first one is both are limiting, both are same in quantity, no reactant is left over, only salt. In the second condition, excess acid, excess acid and less base. So acid will be left over, salt will be left over. Salt will always be available. Salt will always be available. But question is which is left over in the reactant side. First example, no reactant left over. Second example, acid is left over. For a acid buffer, weak acid, salt is required and it is meeting the condition. Third example, the base is extra. So strong base and salt. So strong is not required for buffer. Is it understood now? This is one example. Then one more example is also there if it is a polyprotic. If it is a polyprotic. Okay. Now let us take Na2CO3 plus when it is added with H2O. Then what it will form? NaHCO3 plus NaOH. Okay, NaHCO3 plus NaOH. This is mostly required for advanced exams, so you have to be very careful. Okay, now here it is salt and it is acid. Okay, so it is a salt of weak acid, that is carbonic acid, and it is acid because of this. Because of this hydrogen, it is acid. Understood? So here which should be left over? This acid also should be left over, and salt also should be left over. Okay. If at all the Na2CO3 converted into NaHCO3, then it got capacity to further undergo reaction. Okay. NaHCO3 can further react with H2O to form Na2CO3 plus H2CO3 plus NaOH. Okay. So now here which is acid, which is salt? The same here we took it as acid now, but here it is salt. Which is acid here? Here this is acid. Understood? So same thing can act as acid salt. That is why buffer topic is very difficult. Okay. How to utilize them, how to calculate them, that in the numerical session you will have a clear idea. Okay. When to take acid, when to same substance, reaction changed, you have to treat it as sometime acid, sometime it as a base. Same NaHCO3 in this reaction acid, same NaHCO3 in the same consequent reaction, even not different reaction. Next step itself, its role changed because of the people around it. Previously, the people around it was NaOH. Now, people around it is water. Okay. So when surrounding substances also changes, it changes its nature. Understood? Okay. So this is about the theory part. Let us see in the next numerical session. Bye.